At the start of the previous chapter, we looked at how molecules with leaving groups, particularly alkyl halides, could undergo a substitution reaction just by swapping out that leaving group with the nucleophile. At that point, I had also mentioned there's another way you can go with these alkyl halides, and that is to do an elimination reaction and turn them into alkenes. So that's what we're going to do in this chapter. So since we're starting with the same substrate, with the same reagents, uh, there's often a competition between substitution reactions and elimination reactions, and that's something we will get into in this chapter, looking at how we can determine under which conditions we can sort of force one product versus the other. Okay, so uh, basically the basically the difference between a substitution and an elimination uh, in terms of the reagents you pick is that you'd use a base instead of a nucleophile. All right. So the key thing is that having a base versus a nucleophile is one way that kind of drives an elimination versus a substitution. Things get a little bit more complicated when you have a reagent that can act as a base or a nucleophile. So let's look at hydroxide, for example. Hydroxide, we've seen in the previous chapter, can act as a nucleophile, but it's obviously also a base. We've seen metal hydroxides act as bases, way back in Gen Chem. So again, you want to consider that both these reactions are possible. But basically here we have a alkyl halide, all right, and we can have our hydroxide ion come in and act as our nucleophile here, do an SN2 mechanism, SN2 substitution, and make the corresponding alcohol. Or, instead of acting at the alpha carbon, if we act at the beta carbon, where the hydroxide ion plucks off a proton, forming a water molecule, and then this leaving group leaves, we wind up forming a double bond between the alpha and beta carbon. So these hydrocarbons with double bonds are known as alkenes, or just in general, that a carbon-carbon double bond is known as an alkene functional group, and these are pretty common functional groups. Okay, so back in the chapter on alkanes, when we first started talking about hydrocarbons, we talked about how we could acquire these from crude oil. Alkenes are also, acquired in that same process. They're often the products of cracking crude oil or petroleum. Okay, so you can see that they are pretty good starting points for a lot of reactions. The reason for this is that we can do addition reactions across the double bonds of our alkene and add interesting functional groups that way. We'll get into addition reactions in a later chapter, but my point here is that alkenes are really useful starting points for a lot of synthetic steps, and having them come from something as basic as crude oil is kind of important. Okay, let's talk about nomenclature. You'll find that the nomenclature for alkenes is very similar to what we've already seen with alkanes. So we're still following IUPAC rules for naming these. We're still going to go with that trend of looking for our longest continuous chain of carbons, also known as our parent chain. The only caveat here is that we want to make sure that we select the parent chain in such a way that it contains the carbon-carbon double bond. Okay, so if there is a longer chain that skips the bond, we can't select that as our parent chain. You have to select the longest continuous carbon chain that includes that double bond. Okay. Now the other change here is that when it comes to numbering locants, we typically try to give our double bond the lowest locant. Okay, so we start numbering from the end closer to our double bond. Okay, and then other than that, instead of that ane suffix for alkanes, we end with ene. Right, so something to keep in mind there. So let's go through each of those rules. So here you can see with a 5-carbon chain, 1, 2, 3, 4, 5, this would be pentane, but here we have a double bond in there, so it becomes pentene. Okay. More specifically, we would call this 1-pentene, and we'll see why later. Okay. Here's what I was talking about, selecting that the carbon chain that includes the double bond. If the double bond were somewhere in this longest chain, we'd have an octene and no problem. But the problem here is that the double bond is over here on this branch. And so even though this branch has only 7 carbons instead of 8, we still have to select that as our parent chain. And this becomes heptene, not octene. So as I said, you want to select, start numbering your carbons from the side closer to your double bond, even if that violates some of the other rules we picked up when looking at alkane nomenclature. All right, so even if you have a numbering from the other side would get you to a substituent sooner, or numbering from the other side gives you a lower set of numbers for your substituents overall, you still have to number from the side closer to your alkene, okay, even if it winds up violating that for the others. These other substituents wind up having higher locants, and that's okay. I mentioned earlier that you want to include a locant for the double bond. Okay, you want to say where it is. In some alkenes, it doesn't matter. For example, if you have 2 or 3 carbons in your alkene, your double bond is automatically considered between carbons 1 and 2. That's, again, based on the earlier rules we've discussed. That's where it has to be. But anything more than 3 carbons, and you now have choices for where you can put that double bond. And therefore, we need a locant to say where that double bond is. So instead of naming both the carbons that your double bond is across, you give the lower number for the 2. So for example, here the double bond is between carbons 2 and 3, so we would call this 2-heptene for our 7-carbon chain. Now, you could also insert that locant into the name, the root name, right before that ene suffix. So hep2ene is also a correct way to write that out. Okay. Now, in my experience, I find that listing the locant first before the full name is more common. This saying hep2ene does sound a little bit weird sometimes. But that being said, sometimes based on the types of substituents you have, it's just more convenient to use that alternative method. So watch out for that. There are sometimes examples where it's just more convenient to do that, but you should be prepared to see names like that anyway, or recognize names like that. Okay, so let's try a practice problem out. Okay, so if you look at this molecule now, if this were an alkane, you would have to look at the size of this ring and the length of this longest carbon chain and decide which one would be your root word. This 6-membered ring, the cyclohexane, would have been bigger than 1, 2, 3, 4 carbons, so that would have been a butane. So this would have been considered a butyl substituent on your cyclohexane. However, now that we're looking at double bonds, we've got to look at the longest carbon chain containing that double bond. But again, remember, a cyclic compound or a cyclic substituent can't be considered part of a carbon chain. Okay, you've got to look at this cyclohexyl group as a substituent. Okay, so with that in mind, pause this video and take a stab at this one, and then I'll continue on in a second. Okay, so if you've already tried this, hopefully you've noticed by now that the longest carbon chain has, if we start off not counting the cyclohexyl group, we have 1, 2, 3, 4, 5 carbons. So that would be considered a pentene. Okay, so you want, moreover, that double bond is between carbons 1 and 2 here, so that would be 2-pentene. Like here, I can number these to help out keeping track of that. So we've got 1, 2, 3, 4, and 5. I mean, you could have numbered any one of these as 5, and that'd still be correct. You'd still get the same naming for everything. You've just got 2 methyl groups and that number 4 carbon. Again, notice that we're numbering from over here, not from the other end, because that would then give us our that would put our double bond between carbons 3 and 4, which again we can't do. Okay, so if you look at our substituents here, so we have two pentene, that's our root word, right? We've got two methyl groups, and here let's write this out so you can see all of this. So we have our 2 pentene, so we're kind of working backwards. Okay, start off with that root word, and now let's list out our substituents. We have methyl groups at the number 4 carbon. We've got 2 methyl groups, so that'd be dimethyl, which we'd alphabetize under M. We also have a cyclohexyl group. Okay, so we're going to alphabetize that. If I remember correctly, I think the C actually is what we alphabetize that with, not the H for hexyl. Regardless, either one would come before methyl. So we would have, our 2-cyclohexyl. Okay, and we have 4,4-dimethyl 2-pentene. Okay, or you could have correctly said also pent-2-ene, and that's also acceptable. Now, we've accounted for all the substituents on this carbon chain, on this molecule. The only thing we have not discussed is the stereochemistry around this double bond. Notice that we have 4 different substituents on this double bond, which means this is this has geometric isomerism. The only problem, though, is we would have needed 2 groups on the carbon-carbon double bond that are identical in order to list this as being cis or trans. So over here we would actually have to use sort of EZ notation to say which group this is. We'd have to assign priorities to the 4 groups we have attached here, and accordingly list whether it's E or Z. So for now, I'll just point out that this is going to be an E isomer, but I'll explain what that is later and how to do that later. Oops, I went to the next slide. Made a slight mistake there. I forgot to put parentheses around the E notation. So just quick note here that when you write out that E or Z distinction, unlike cis or trans where you just write out cis or trans and have a hyphen, here I would have put that E in parentheses and then continued on with the name. So, 2-cyclohexyl, 4,4-dimethyl. There we go. So sorry about that. You need to put parentheses around your E there. Okay, so getting back to alkene isomerism. So just again, continuing on this topic, you've already seen cis and trans isomerism before. So just to jog your memory, if you imagine your double bond being kind of imagine a dotted line sort of running parallel with that alkene, with that double bond. If you have your identical groups on the same side of that border, that's cis. If they are on opposite sides, that's trans. Okay, so just remember that when you're looking at the geochemistry around alkenes. Of course, though, as I pointed out earlier, you've got to consider when you don't have 2 identical groups. In the case of cyclic alkenes, sometimes you're forced to have the cis alkene as opposed to trans, right? The reason for this is that due to just the geometry of the shape, you're kind of locked into that cis geochemistry. So notice that, for example, in cyclopropene, these 2 carbon bonds have to be angled this way on the same side of that double bond. It's impossible to have a carbon-carbon bond to this carbon over here, have a bond going in the opposite direction. It's just physically impossible. So typically, anything less than 8 carbons in your ring will result in a trans alkene being unstable. It's just too much ring strain to preclude that. Okay. Once you get to 8 8 carbons or more. So for example, here we have trans cyclooctene. So we have 8 carbons with a double bond in there. Now it's possible to have these 2 carbons going off in opposite directions and still wind up having the carbon chain link back together. Okay. Now, in the case of bicyclic alkenes, this is called Brett's rule. Okay, so here's an example with Brett's rule, specifically with a bicyclic compound. So you can see here we have a 6-membered ring including our alkene, and so we know that this is going to be this is not going to be stable. But here we have an 8. Actually, wait, 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8. Yep, we have an 8 carbon ring with an alkene, and again, notice that our carbons here are trans, right? They're going in opposite directions from that double bond, and but that's allowed with Brett's rule. Okay, whereas here that trans configuration is not going to be stable, just in terms of the ring strain that's going to be on these bonds is going to be huge. Okay, so let's talk a little bit about that EZ notation I mentioned. Basically, with cis and trans, you can only do it with when you have comparable groups. So for example, I would call this trans 2-pentene because I have a hydrogen here and a hydrogen here. That shows me that, well, my hydrogens are on opposite sides of my double bond. But if we have 4 different groups, now this gets complicated because we don't know, we don't have a way of saying, like, we can say that 2 groups are cis to each other, 2 groups are trans to each other, but there's no way to inherently make that clear when writing out a name for something, right? You could if you're writing a paragraph describing the molecule, but it's kind of silly to do it in just a name. So that's where EZ notation comes in. All right, so here you can see we've got an example of 2 isomers where 2 geometric isomers, right, where we've kept these 2 groups over here identical, but we've flipped the hydrogen and the amine group on the other carbon of our double bond, right? So these are obviously not identical molecules, but they have the same components. They're just they're geometric isomers, right? So we need to assign priorities to these groups and then essentially say whether they're, quote unquote cis or trans, but by referring to those higher priority groups. But we can't say cis or trans because it's not, because obviously it's not the same group, so that's where E and Z comes in, right? So E and Z notation is essentially cis and trans, but for non-identical groups. Okay, so let's look at how we do this. Basically, you look at the atoms directly bonded to your double bonded carbons, and you assign them priorities based on atomic number. So over here we have a carbon, here we have a fluorine. The fluorine's going to win. Okay, so that is the higher priority group on this carbon. Now let's look at the other carbon of our double bond. We've got a hydrogen, we've got a nitrogen. Nitrogen, of course, will definitely have higher priority than hydrogen. Literally everything has higher priority than hydrogen, so nitrogen wins. Now, do we call this E or Z? Okay, they come from German words, and basically, this is going to be kind of silly, but the way to to remember which one's which is this has Z notation because they are on the same side. That's one way to remember it if you don't want to remember the German word zusammen. But basically, that's how you can remember which one's the Z isomer. It's where both of your high priority groups are on the same side of your double bond. Okay, so it's cis, so to speak. Okay, so yeah. So again, E of course is if it's on the opposite side. So again, I've probably mispronounced that horribly. But anyway, so I mentioned earlier that typically trans isomers tend to be more stable. And the reason for this is that the bulky groups in a trans isomer tend to be apart from each other, right? And that stops them sort of clashing with each other without having their electron clouds repelling each other. Okay, so you can see that a little bit here in the example of cis-2-butene. where you've got that strain between the two methyl groups on both ends of your carbon chain, right? You can see that if you look at a space filling model, there's some steric strain there by having these groups sort of clash with each other. And we don't have that problem with the trans isomer. So we can see this. We've done this before, where we've looked at heats of combustion and used that as kind of a metric for determining which molecules are stable, right? Because the more stable something is, the lower its potential energy, and therefore the less heat it gives off when it gets converted to the even lower potential energy carbon dioxide and water vapor. Okay, so you can see here that trans 2-butene has a lower heat of combustion compared to the cis isomer because it had a lower starting point when it dropped down to carbon dioxide and water vapor. So you can kind of see it visually here, right? So since we're at a lower potential energy for that trans isomer because it's more stable, that's why, you know, we get less energy when it becomes carbon dioxide and water vapor. Okay, and again, we can use this to quantify the stability difference between the two isomers. The fact that the cis isomer gave off 4 kilojoules per mole more heat tells us that it's 4 kilojoules per mole less stable. So with that in mind, the other thing to notice when it comes to stability of alkenes is that the more substitutions actually increase stability. Now, I know that seems kind of counterintuitive based on what we just said with steric strain, but ignoring steric strain, or like looking at that as a separate factor, the number of substituents generally increases stability. Remember, alkyl groups can kind of push electron density towards something due to hyperconjugation. We saw this back in when we were learning about carbocations. So it turns out that this basically these alkyl groups kind of stabilize sp2 hybridized carbons in a similar way. So with that in mind, let's try a little practice problem. Go ahead and draw out these 4 molecules and see if you can rank them from, in terms of increasing heat of combustion. In other words, from your most stable to your least stable out of the 4 of these. Okay, so feel free to pause this video and we'll come back to this problem. Okay, so let's first of all, let's try drawing these molecules. So if you haven't done that yet, feel free to follow along. Well, actually, it looks like here we've got 2 5-carbon, or start off with a 5-carbon chain. So we've got 1,3-pentadiene. So let's start off with our pentane here. 1, 2, 3, 4, 5. Okay, and we have double bonds on 1 and 3 carbons. So between carbons 1 and 2, and between carbons 3 and 4. Okay, so there's our 1,3-pentadiene. And we have methyl groups on the 2, 3, and 4 carbons. So that's a methyl group on the number 2 carbon, number 3 carbon, and number 4 carbon. Okay, so that's that molecule there. Let's now try drawing 2 isopropyl 1,4-pentadiene. So again, start off with our pentane, 3, 4, 5. And here we have double bonds at the number 1 position, so between carbons 1 and 2, and at the number 4 position, so it's between carbons 4 and 5. We have an isopropyl group, it looks like, at the number 2 position, so that would be over here. So there's our isopropyl group. Okay, so that's going to be our pentadiene molecule. Let's use some of this empty space down here, actually, since I've got so much room. 1,5-hexadiene, so 1, 2, 3, 4, 5, 6, and we need a double bond at the 1 position, and 1, 2, 3, 4, 5 at the 5 position. And we've got 2 methyl groups in the number 3 carbon, so that would be down here. And then this guy over here is going to be a cyclohexene. Notice that there's no locant for cyclohexene because it's understood that the double bond is between carbons 1 and 2. Okay, because we've got a ring and your lowest priority goes to the double bond, your double bond's automatically at the number 1 position, so it's kind of silly to say 1 cyclohexene. It's obviously going to be 1 cyclohexene. Okay. We have methyl groups at the 4 and 5 position. So 1, 2, 3, 4, 5. There's our 4,5 dimethyl cyclohexene. Okay, so if you hadn't drawn these molecules, well, now you've got them in front of you. So again, feel free to pause this video and see if you can figure out which ones are the most stable. Okay, my advice is to look at all of your double bonds and ask yourself, how many substitutions do we have around each of them? Okay, so if we look at this double bond, for example, there's a carbon coming off it here, carbon coming off of it here, but these are two hydrogens. So this would be a di-substituted um, double bond. Likewise here, we've got 1, 2, 3, 4 carbons. This is a tetra-substituted double bond. Okay. If we look at this one, we've got di-substituted, and this one's just mono-substituted. Okay. Here, again, we have 2 as a di-substituted. Here we have mono-substituted, and this is also mono-substituted. All right. So you can see that this one clearly has a lot of substitution. So this is probably our most stable here. Okay, so I guess if we're ranking these, rank this number 1. Okay, now if we look at our other double bonds, this one's got a di substitution and a mono substitution, and this one's only got a di substitution. So these two are probably going to be in the middle, whereas this one with only primary substitutions, like mono substitutions, is going to be probably the least stable. Okay, so now let's look at how elimination reactions work in more detail. So if we, basically we want to remove our leaving group from our alpha carbon and a proton from our beta carbon, and that's where we form the double bond of our alkene. Now, to understand this fully, let's think back to some of those steps that we saw in previous chapters that are behind all mechanisms. So we have, of course, the 4 steps of a nucleophilic attack, the loss of a leaving group. If you recall, both of those are important for or are essential for substitution mechanisms. And of course, we have proton transfers and carbocation rearrangements, which also might be involved when it comes to substitution reactions. Okay, so just as a visual, here are the 4 different steps. And of course, remember, nucleophilic attack and a leaving group leaving are kind of reverses of each other. All right. Now, let's think about how this applies to an elimination reaction. I mentioned earlier that these 2 steps over here, nucleophilic attack and a loss of a leaving group, are both essential for a substitution reaction. What about elimination reactions? What are the essential steps that we see in our elimination reactions? Well, if I go back a slide, you'll remember I pointed out that we lose a leaving group, and we also lose a proton. So those 2 steps, the loss of a leaving group and a proton transfer, are going to be very important here. In fact, those are the 2 key steps you need for an elimination reaction. Okay, so just like we had a distinction between SN2 mechanisms and SN1 mechanisms, we're going to have a distinction here between different types of eliminations, specifically what we call an E1 elimination and an E2 elimination. Okay, so very similar naming for these processes you can see here. So just like an SN2 mechanism is a concerted one-step process where we've got 2 molecules involved in the slow step of the reaction, because it's the only step of the reaction, we could also do our elimination in one concerted step where a base comes in, plucks off a proton, and simultaneously, as those electrons move around, that causes the leaving group to leave. Okay, so in one step involving 2 molecules, our base and our substrate, we make our alkene and we have our leaving group. And what's not shown here is the conjugate acid of our base leaves with the proton as well. Now, we could also have this done in 2 steps, just as we saw with an SN1 substitution, where you first have your leaving group leave, all right, creating a resulting carbocation, and then a base comes in, plucks off that proton, and forms the resulting alkene. Okay, so you can see a lot of parallels here between how our SN1 mechanism starts. It actually starts with the exact same step. You have a leaving group leaving to make a carbocation. The only thing that's different is that instead of your nucleophile attacking that carbocation, you have a base plucking off that proton. As I mentioned, we have specific names for these mechanisms, and the process for naming them is kind of as well very similar to that for nucleophilic substitutions. We have a 2 for our E2 mechanism because there are two molecules involved in that slow step, the only step of this mechanism. Okay, so we're first order in both the base and the substrate when it comes to looking at the rate law for this mechanism. We saw back in SN2 substitutions that having a very hindered alpha carbon is detrimental to that SN2 substitution because it makes it really difficult for that nucleophile to come in and attack that alpha carbon. There's just too much steric hindrance around it, right? But in the case of an elimination reaction, this isn't as big of a deal. Okay, this isn't as big a barrier to a successful reaction because your base that's coming in isn't trying to attack your alpha carbon. It's actually going for that beta carbon. It's plucking off a proton from that beta carbon, which need not necessarily have, be tertiary. Okay. So something to keep in mind there when you're looking at whether your substrate is primary, secondary, or tertiary. Remember that designation's referring to the alpha carbon, and in the case of an elimination, that's not as big a deal. Now, so in that being said, we actually see the opposite trend compared to what we saw in SN2 mechanisms, where tertiary substrates are actually more reactive, even though there's a lot of steric hindrance in just one carbon away. And we're going to see why in a second. If you recall, when looking at the preference of one mechanism over another, there are two ways to look at it, right? We want to look at either the activation energy to determine if it's a kinetic product that's favored, or at the stability of the product, looking at the potential energy of that to determine if the thermodynamic product is preferred. In the case of if using a tertiary substrate for an E2 mechanism, it turns out that both your product is from a tertiary substrate is considered both the kinetic and the thermodynamic product. Your activation energy is lowered, as well as the potential energy of your product. Your product's more stable when you have a tertiary substrate. Okay, so if you want to compare a reaction coordinate diagrams, notice that with a primary substrate versus secondary substrate versus a tertiary substrate, the tertiary substrate has a lower potential energy than the others, and its product is more stable compared to the other products. Okay, the reason for this, of course, is that if we look at that transition state, if I go back a slide, the extra alkyl groups on that alpha carbon stabilize the partial positive charge that's on that alpha carbon. So that would lower the potential energy of our transition state and therefore lower the activation energy. All right, therefore making the tertiary substrate give a kinetic product. Now, in the case of our resulting alkene, though, having more alkyl groups will increase the number of substitutions on your product, which, as we've seen earlier, makes a more stable product, and therefore you have, a thermodynamic product here as well. Okay, so in general, we've got multiple reasons driving, speeding up the reaction for a tertiary substrate when it comes to E2 eliminations. Now, that being said, oftentimes we have more than one option for the proton that we deprotonate. And as a result, we can sometimes get different types of products. The location of the double bond might be different depending which beta carbon you take a proton from. Okay, so here's an example with 2-methyl, 2-bromo, or 2-bromo, 2-methyl butane. Okay, so notice that we would lose our bromine, but we've got two beta carbons, actually technically a third one here that's also beta carbon, but it's identical to this one down here. So we've got essentially two different options for where to form our double bond. We could form the double bond between this alpha and beta carbon, or between the alpha and this beta carbon. Okay, and those are the two products we observe. Now, the difference between them is what we call regioselectivity. All right, how do we encourage one of these products versus another? First of all, you should probably get comfortable with the names here. We call the more substituted product the Zaitsev product. Okay, sometimes also spelled with an S instead of a Z. We also have the Hoffman product, okay, which is less substituted. Okay. Yeah, with Zaitsev, I think you sometimes see it with an S, and I think with a Y as well. It's spelled. There's definitely multiple. I believe it's SAYTEFF, or there's definitely a lot of misspellings for Zaitsev. Anywho, we can see that the choice of base affects the regioselectivity. All right, so notice that here with ethoxide as our base, we use sodium ethoxide, for example, we have a preference for the Zaitsev product. But if we use something like tert butoxide or an even bulkier base like this one, notice that the Hoffman product winds up getting much more preferred. Okay, so think about why that's the case, right? So why does a smaller base prefer the Zaitsev product? Why does a bulkier base prefer the Hoffman product? Okay, so think about the transition state and go from there. All right, so here's some examples of some bases that prefer the Hoffman product. As I mentioned, they're kind of bulky, also called sterically hindered. And we've got lots of options here. I think the butoxide ion is probably the most common one you've seen. But it's possible to get certain amines that have bulky alkyl groups on them. If I go back a slide here, and just to help you understand what's going on, remember, the Zaitsev product is more substituted, right? So if we were going to compare the thermodynamic feasibility of each of these two products, the Zaitsev product would be the thermodynamic product, right? It's the more stable of the two. Okay, so I think the Zaitsev product, all things being equal, would be more favored, assuming that your transition state doesn't favor the Hoffman product. So that tells you that the transition state for a Hoffman product probably gets encouraged because the competing Zaitsev product for it would have too high a transition state. So remember, it's the bulky base that prefers the Hoffman product. And so the reason that this is a little bit more difficult for the it's more difficult for a bulky base to form the Zaitsev product is that beta carbon you remove a proton from to make the Zaitsev product is more sterically hindered than the beta carbon that you would eliminate deprotonate to make the Hoffman product. Okay, so it's easier for a bulky base to access this beta carbon than it for a bulky base to come in here, where this extra methyl group is sticking out. Sorry, over here. Okay, so that's basically what it comes down to. Using a bulkier base kind of forces that less thermodynamically favored product. Because it just has easier access to that beta carbon and therefore a lower energy transition state. But that being said, all other things being equal, a regular base, a smaller base would prefer the Zaitsev product because it's more thermodynamically stable. Let's also consider stereoselectivity of elimination reactions. Now, we mentioned that we just talked about regioselectivity, so we talked about where the double bond's located. We're now going to talk about the orientation in space of that double bond. Do we basically get a cis or trans product? Okay. Now, we mentioned earlier that the trans product is typically more stable, okay, because you have your bulkier groups are further away from each other, okay, and so there's less steric hindrance between them. Then with the cis product, there's some steric hindrance here, okay, between like the hydrogens coming off this carbon and this carbon, right, for example. Okay, so that's why your major product here is your trans product, because it's just more stable. you'll notice also looking at this reaction coordinate diagram that the transition state for the trans product is also more stable. So the reason that the transition state for your trans product is a little bit more stable actually also has to do with your bulky leaving group, right? So your leaving group is typically a relatively bulky group to help stabilize that, that negative charge it's going to take with it. So in the case of making the trans product, the protons you're deprotonating on that beta carbon are pointed away from that bulky bromine, whereas on the cis product, you have this methyl group flipped up over here, and so your hydrogens would be over here, down here, and so again, you've got some steric hindrance from that bromine for your base coming in trying to deprotonate that carbon. In addition to stereoselectivity, we also have stereospecificity. Okay, so when you look at the orientation of of a molecule like this, there's only one beta hydrogen to be removed. But what if you had if you had multiple options? How do we figure out which one is selected to give the product that we see? In other words, if we have multiple options there, how do we know if we're going to make the cis or trans product, or E or Z as the case might be? Okay, so it turns out, for example, in this example here, we wind up seeing the only the E product, right? Remember, you can freely rotate around this carbon-carbon single bond. So you see, but instead of getting a mixture of products, cis and trans, we wind up getting exclusively this one. Now, to understand, you could make a stereoselective argument that, like, oh, that you've got the bulky groups trans to each other, that's more stable. But there's actually a stereospecific argument here that has to do with the orientation of your leaving group and your proton in three-dimensional space, in your transition state. So let's have a look at that argument. Okay, so if we look at that bromine leaving group and the hydrogen that we're looking at, as well as the two carbons that are attached to, if we connected the four of them, we could form a plane with them. Okay, so if we have them all in the same plane, that's a possibility. I mean, you could rotate around this carbon-carbon bond and break that hydrogen out of the plane, or the bromine out of the plane. But typically the transition state you want for this has to have everything in the same plane. This allows orbital overlap and so on. So basically it looks kind of like this, like your bonds are breaking and in this case forming, in the case of your pi bond. And for the orbitals that are involved there has to be an overlap, and so everything needs to be coplanar, has to be in the same plane. All right. So essentially, to be coplanar, you have two options here, right? You could be anti-coplanar, where the hydrogen and bromine are anti to each other, if you were looking down that carbon-carbon bond, or they could be syn, they're kind of overlapping each other, right? In an eclipsed formation here. We actually see the anti one exclusively. Just from a steric standpoint, you've got some steric hindrance from this bromine here, but also you've got to consider that this is an eclipsed transition state. So all of these bulky groups are, overlapping each other essentially. Okay, so you can kind of see it in this picture here, right? So here we have the anti-coplanar geometry, where we've got a staggered geometry, and here with the syncoplanar, this is an eclipsed geometry. So there's a lot of steric strain there between these groups. Okay, so it makes sense to have the anti-coplanar geometry be the transition state that we see. Well, if your hydrogen and bromine are anti-coplanar to each other, that dictates where those other groups are going to be in the resulting alkene. Okay, so if your methyl and terpyl group are on this side, are on the same side here, and your benzene and hydrogen are on the same side here, they'll be on those same sides for your resulting alkene. Now, I say anti-coplanar. In real life, it doesn't have to be exactly coplanar, right? They don't have to be perfectly in the same plane. There's a little bit of wiggle room in there. So instead of saying coplanar, we typically say periplanar. I think I slipped up earlier and accidentally said that out of habit. But really, you need anti-periplanar geometry, and that is sufficient to have the low energy transition state that gives you the product that you see. Okay. So even though you could argue that that E isomer from a stereoselective standpoint is more stable, and therefore you're going through a less hindered transition state because of that, you need the anti-periplanar transition state, and so sometimes it is possible to get a Z isomer or a cis isomer, even though it seems like a little counterintuitive. Okay, so the key, it's more important to have that anti-periplanar transition state than it is to have a trans or E product. So with that in mind, have a look at these these examples here, right? So here we've already set up the proton and the bromine to be anti-periplanar to each other, or anti-coplanar as they're drawn here. So based on where groups R1 and R2 are, you could get a feel for those alkenes. Notice that here in this top one, groups R1 are both pointing towards you, groups R2 are pointing away from you. Okay, so they'll be each on the same sides. So you'll have both of your R1 groups on the same side and your R2 groups on the opposite side. Okay, oops, I guess I don't have that drawn there. So it'll look kind of like this. So if I were looking down on this, okay, so these, so this carbon was on top for me and this one was on the bottom. So I was looking down at this. These R1 groups are both on my right, and these R2 groups, which are sticking away from us, would be to my left if I were looking down on this molecule. Okay, so notice that we have a cis molecule being made here, despite the fact that that's often less favorable. Okay, here you can see that we've got our anti-coplanar geometry or anti-periplanar, and here R1 on the bottom carbon is to my right, and R2 on the top carbon is to my right. So it would look like this. Okay, so those groups that are pointing towards me is R2 and R1, and on the left of me, so if I'm looking down here, and this is my top carbon, like my head's pointing this way. So this is my top carbon, that's my bottom carbon. R1 is going to be pointing to my left, and this R2 is pointing to my right. Also pointing to my left. Okay. So notice that here we have a trans isomer, and here we have the cis isomer. Okay, so it's not so much the groups that are involved. It doesn't matter what R1 and R2 are. It's what's more important is that anti-periplanar relationship between our proton that's being plucked away and our leaving group. Okay, but that being said, we sometimes have more than one option on that beta carbon. So that's something to keep in mind for what products you could make. Okay, so you've got to consider that there are two possible products here, and then you might want to look at the stereo selectivity of the resulting alkenes you make. So again, getting the bulkier groups apart from each other or trans to each other would be more preferable. Okay, and that might give you a major product accordingly. Okay, so now let's look at cyclohexane, right? So you have cyclohexane with some leaving group. How does that affect anti-periplanar geometry, right? So do we need, is it better to have our axial or equatorial orientation for our leaving group and our hydrogen? Well, in order to see that anti-periplanar geometry, again, looking at this Newman projection, remember, those two groups would be anti to each other, okay, in the staggered conformation. Notice that we lose that when there are chlorines at the equatorial position, okay? So notice that we want this to be axial, and notice that the beta proton we're going to eliminate is 1 carbon away. So we actually have 2 options here. It could be that hydrogen's pointing down over here, or the hydrogen that's pointing down over here. Okay, so with that in mind, you have to realize then that this affects what what our product's going to look like, and might actually limit the number of products we can make. So when you look at your leaving group, you've got to remember that you need a proton that is anti-periplanar to it on those beta carbons. If you don't have an available anti-periplanar proton, you're not going to do an elimination on that molecule. Okay, so you can't just look at a molecule or just like assume that all of these molecules are going to undergo E2. Here, in the case of these cyclic compounds, they're locked into place, and you've got to do a little bit more investigating to decide, like, okay, is this going to undergo, is this going to affect what type of product I make? So if we look at this example here on the left, notice that we have 2 protons here. One of these is going to be anti-periplanar to our chlorine. So, we're definitely going to be able to form a double bond here to the right. I guess the question you should ask yourself is this proton over here going to be anti-periplanar to this chlorine? Okay. So if you don't have a handheld model to make, you can use our up-down notation to kind of figure out what's going on. So remember, we want our 2 groups to be axial, right? So if this, let's say the solid wedges are pointing up towards us, okay? So in order for this chlorine to be axial, this has to be an up carbon. Okay, so up carbon, up chlorine, this is going to be axial. Okay, which means these beta carbons next to it are pointing downwards. Okay, and remember, for an axial position, we need down, down. So in this case, this hydrogen is in that position, which means it will be anti-periplanar to this chlorine, so it is possible to form a double bond here. And coming back to this one, I mentioned that one of these would be anti-periplanar, and it turns out it's going to be this one. We want this one to be down, down to be axial as well. Okay, now let's look at this molecule here. Again, same orientation of that chlorine, so this is up, this is down. Now notice that the thing that's anti-periplanar to the chlorine is actually the methyl group for both of these carbons, which means that the hydrogens here are not anti-periplanar, right? So that means that this will not undergo an elimination reaction. Okay, at least not an E2 one. So there you have it. So, that's something you've got to be careful or be at least aware of when you are trying to figure out, 1, what are the products you're going to make, and 2, are products even possible? So here, like, we can't, deprotonate at either side. Okay, if this hydrogen, this methyl group were flipped, we would see that we would only get a double bond on this side. We would not form the double bond on the other side. Okay, so you can kind of see that here now. So let's go through some practice problems here. Okay, so look at each of these 3 alkyl halides that have alkyl groups in ring compounds, right? Which again, remember, limits our options. And go ahead and figure out what the product would be when we do an E2 elimination. Okay, so in this case, our chlorine is going to be is pointing. Let's say that it's again like. Let's say this is up to make this axial. We want a hydrogen that's pointing downwards on those beta carbons. Now in the case here, that methyl group's pointing downwards, so there can't be a hydrogen in that location. The hydrogen here is going to be equatorial because it's pointing upwards towards us. So we do not see a double bond forming on this side. Instead, we only see a double bond on this side here because out of the 2 hydrogens here, one of these is going to be one of these has to be anti-periplanar to this chlorine. So we only see the double bond here. We do not see a product where there's a double bond here. Okay. All right. So let's have a look at some of these other ones. Here, actually, I can just go through the answer slides like that. So here for this one, we actually do see both products. So if we look at our leaving group here. Here's our chlorine. Now let's look at both of our beta carbons. Okay, now in this case, we've got 2 protons on this beta carbon. You're definitely going to be able to form a double bond here because one of these will be anti-periplanar. So that's this product we see over here. What about this proton here? Is this anti-periplanar to our chlorine? So again, if you have trouble seeing this, I haven't done this for any of the others, but if you do have trouble seeing this, just draw in that hydrogen and ask yourself, is it anti-periplanar to that chlorine? Again, the key thing to realize here is that if this is pointing up, up, we want this to be down, down. So in other words, this proton needs to be trans to this leaving group, okay, which it is. Okay, so that means that's why we do see this product. Quick point here, because this is a mistake a lot of students often make when trying to draw this by hand. Notice that we lost the wedge for this isopropyl group here. The reason for that is that this carbon is now sp2 hybridized. This is trigonal planar. This is going to be completely flat. So this isopropyl group will not be pointing towards you. Okay, so something to watch out for when you're drawing this. Okay, always be aware of, the geometry of those nearby carbons, and you only really need wedges if you have an sp3 hybridized carbon. Okay, then for this last one, again, we've got our leaving group here. Look at where your beta protons are going to be. Again, with this one down here, we're definitely going to be able to form a double bond because there has to be something that's anti-periplanar. One of these 2 hydrogens is going to be anti-periplanar to this leaving group. Over here, for this hydrogen that's not shown, notice that this is cis to this chlorine. So this is not going to be anti-periplanar, and we can't form the double bond over here, and that's why we don't see that product. We only have this product where the double bond forms over here. So with that in mind, you can then combine these effects. Okay, so that's something to keep in mind in general. So have a look at these 2 reagents. So over on the left, we use sodium ethoxide, which is a smaller base, and on the right, we have sodium tert-butoxide, which is a bulkier base. Okay, so think about how that drives the Zaitsev versus the Hoffman product that we're looking for here. Okay, so take a moment to think about those. Okay, so if we look at the 2 products we've got here, okay, with the smaller base, the sodium ethoxide, okay, we have we're going to make a Zaitsev product where it's going to prefer to take this this proton that's attached to a that has a methyl group next to it, right? So even though there's a little bit of steric hindrance there from that methyl group, your ethoxide is small enough to access it. Okay, now the question you should ask yourself before you think about this is that proton anti-periplanar to that chlorine, which it is, right? If that's pointing down and away from us, well, this one's pointing up and towards us, so they're trans to each other, so they'll be anti-periplanar. Okay. Likewise, on this carbon, there are 2 hydrogens, so you take the one that's anti-periplanar, but remember your sodium ethoxide would prefer to form the double bond here because this resulting double bond is tri-substituted. Okay, if you eliminate this proton here, you get the resulting di-substituted one, which is less stable, right? So this is not the thermodynamic product. This one's the thermodynamic product, okay, the Zaitsev product. But instead here, notice that it's easier to access that proton because there isn't a methyl group that's providing a little bit of steric hindrance. Okay, so notice our bulky tert-butoxide prefers to take this one, even though you get the less stable product. Okay, it's just easier to form, even though it winds up being less stable. Okay, so that's it for E2. Let's move on to E1. So with an E1 mechanism, just like an SN1, we have only one molecule involved in that slow step where the leaving group leaves. And of course, the second step is much faster. Instead of a nucleophile attacking, though, we have a base deprotonating that beta carbon to produce the alkene. So again, since that slow step involves just the one molecule substrate, it's first order with respect to that, and unlike an E2 mechanism, the base doesn't affect the rate of the reaction. Zero order with respect to the base. Yeah, basically we still have that formation of that carbocation like we see in our SN1. And so we have the same sort of considerations to take into to keep in mind, and that is you have to watch out for a possible carbocation rearrangement when we look into that. So regarding substrate effects, just like with an SN1 mechanism, we find that a tertiary alkyl halide or a tertiary substrate is going to be much more reactive. Since you're still going through this carbocation transition state, it makes sense that you want multiple alkyl groups attached to that alpha carbon with its positive charge to help stabilize that positive charge. Just like with an SN1 mechanism, you're lowering the potential energy of that carbocation intermediate, and that lowers the activation energy for the process, and therefore you make more product, make product quicker. So you can see the similarities there. So basically it just comes down to, in the second step, do you have a nucleophile acting or a base? Just as we saw in our SN1 mechanisms, it's good to have, it's important that our leaving group leaves to really sort of kick off this reaction, right? The thing that really starts the reaction is getting that leaving group to leave. So if you have a leaving group that's not as good, such as, let's say, an alcohol group, you may have a proton transfer to help encourage that leaving group to leave. So, for example, if you do this in the presence of an acid, you protonate that alcohol group, it can then leave as a neutral water molecule, which is a great leaving group. Okay, so we see this when we use a concentrated sulfuric acid and heat to convert an alcohol into the corresponding alkene. Just using water essentially as your base to deprotonate this beta carbon. You don't want to have anything stronger than that because then it might react with your sulfuric acid instead. Now, in the case of E1 reactions, you typically get your Zaitsev product as your majority. Remember, the thing that drives this reaction, your rate determining step, is that formation of that carbocation. Unlike an E2 mechanism where your base coming in kind of initiates things, it kind of drives the reaction forward, and therefore, if you use a bulky base, that kind of really changes the stability of your transition state, and therefore really encourages one product versus another. Here in our E1 mechanism, we're starting from a high energy carbocation, so there really isn't too much of a variation in the transition state that we're looking at in terms of the difference in energy. So what really drives our product formation is that thermodynamic product. We're going to produce the more stable Zaitsev product, generally speaking. All right, so unlike E2 mechanisms where you have a lot more control over regioselectivity depending on what type of base you use, here E1 mechanisms generally prefer the Zaitsev product. Just the thermodynamic product wins out here. Regarding stereoselectivity, again, we're going to notice that we're going to produce that trans product a little bit more. That's typically more stable. We've seen that already for steric reasons. You're starting off with that sp2 hybridized carbocation, so it's a flat state. So depending on how you rotate around, that carbon-carbon bond to begin with, that can determine where that, when you eventually form that pi bond, which direction your other groups are pointing, and it makes sense that this would be a more thermodynamically stable product as well. So with that in mind, here's an example of an alcohol here. That we're going to have that get protonated with concentrated sulfuric acid and have that leave as our leaving group. Go ahead and consider the products that we would make, both from a stereochemistry and a regiochemistry standpoint. So go ahead and pause this video and take a stab at this problem. Okay, and if you're back, so when our leaving group leaves, we're going to essentially, we're protonating this this alcohol group, and this winds up leaving as a water molecule. So what does the resulting carbocation look like? Well, if I draw the rest of the molecule kind of identically, Okay, so that methyl group sticking out towards you. Then we've got that. All right, so there's oh yeah, there's that methyl group. Um, you see that this methyl group is drawn with a dashed wedge here, but keep in mind it doesn't really matter what the stereochemistry of this is now, because once we have our leaving group leave, and this is an sp3 hybridized carbocation, well, this is going to be trigonal planar, right? So this methyl group is now in the plane of our paper or our screen, so it doesn't really matter which way it points, okay? Now, here's the thing. We are now going to have to pick which beta carbon. We've got three options for a beta carbon. Which one are we going to deprotonate? Well, if we could deprotonate this one, form a double bond here, which would be di-substituted. We could deprotonate here, deprotonate one of these two hydrogens, form a double bond here, and make a tri-substituted alkene. Or notice that there is a proton or a hydrogen over here that we can deprotonate, and if we form double bond here, this winds up being a tetra-substituted double bond, right? Which would be the most stable. Now keep in mind, if we remove this hydrogen that's not shown over here and form a double bond here, this carbon becomes sp2 hybridized as well. So this solid wedge here disappears as well. This would be in the plane of the screen as well. So your product actually winds up looking like this. And we have our double bond here, and these are sp2 hybridized carbons, so there's really no need to show stereochemistry. In fact, you really shouldn't show stereochemistry because these 6 carbons are all in the same plane, okay, because these 2 carbons are sp2 hybridized. All right, so I kind of have said several times that there's a lot of similarities between that SN1 E1 mechanism. This includes the sort of extra steps you might see. So we've seen already in an SN1 process, the key steps you have to have, of course, are the loss of a leaving group and a nucleophilic attack. Now, you could have a proton transfer that makes your leaving group a better leaving group. You might have your carbocation rearranged to become a better carbocation, and then you might have a proton transfer on your final product to make it more stable. Well, we see almost the same things with our E1 mechanism. So you might have a proton transfer that makes your loss of the leaving group more stable, a better leaving group. You might have the resulting carbocation rearranged to become a better carbocation. Okay, now you then have, instead of a nucleophilic attack, of course, we do a proton transfer to make the resulting alkene, and please note that this is a required step. But then at that point, you've made your stable product. There really is, you kind of stop there. All right. So something to keep in mind, though, with some of those extra steps and the similarities that we see. Here's a complete E1 mechanism for this dehydration reaction. Okay, it's called a dehydration because we're essentially removing a water molecule across these, 2 carbons. So, you protonate your alcohol group. So we do a proton transfer, which in this case is necessary to make this a better leaving group. Then we have the loss of the leaving group, which is an essential step for, any elimination reaction. And then the resulting carbocation is already tertiary, so there's no rearrangement there. But we do a proton transfer, from that beta carbon to produce the resulting alkene. Here's an example with a carbocation rearrangement, but that doesn't have a proton transfer to begin. So here we have our leaving group. It's a chloride, that's already a great leaving group. So our leaving group leaves in the first step. We have a secondary carbocation that's formed, but if we do a methyl shift here, we get a corresponding tertiary carbocation, and so that's what happens. We then eliminate we deprotonate that beta carbon and produce the resulting alkene. Of course, there are multiple beta carbons you could select from. This beta carbon is the same as this one, so it doesn't matter which one you deprotonate here, you're going to get the same product. This beta carbon here, of course, would be essentially the Hoffman product, and we've seen there's a strong preference in E1 mechanisms for that Zaitsev product, so that's why we get the Zaitsev product. Here's an example with both things involved. So again, we have our alcohol group, which is not a great leaving group, so we have to start off with a proton transfer to make it a better leaving group. Okay, so we protonate our alcohol group, it leaves as a water molecule, okay, and there's that loss of a leaving group step that's important. the resulting carbocation is a secondary carbocation, and so if you look at its nearby carbons, we see that if we move this methyl group over, we get a tertiary carbocation. Then out of your beta carbon options, this one with its proton here, uh, you eliminate, you transfer that proton there, and you make your resulting um, tetrasubstituted double bond. Okay, as opposed to deprotonating one of these other, carbons to give you the, disubstituted Hofmann product. So yeah, so this is kind of what the energy diagram profile looks like, the reaction profile. So notice that that rate determining step of losing that leaving group is still the rate determining step, right? That's kind of the key thing. We make this high energy intermediate, carbocation intermediate, which, you know, these two steps in blue are steps that might not be present in your mechanism. So the maximum number of steps you have here are 4. But yeah, that's kind of what that would look like. So with that in mind, let's see if we can figure out, do a little practice problem here and figure out what our minor products are going to be. So we can see here's our major product that's formed by, essentially your Zaitsev product with the elimination of this alcohol group. Let's see if we can figure out what else we make based on that mechanism we just saw. So we saw, for example, that carbocation will rearrange, right? It'll undergo rearrangement, and that's what yields us, this resulting product. It's due to a rearrangement. It's one of these methyl groups is actually shifted over to this carbon that our leaving group left from, and that's why we see this methyl group here. That being said, you might, see, you get a tiny amount of that less stable secondary carbocation going on to form product. Okay, so think about what that would be. Likewise, the other minor product you might see is like you have your rearrangement, but instead of getting that Zaitsev product that we expect, we instead get a Hofmann product. So let's go ahead and try drawing those. Okay, so if we have, so if we think about the carbocation we get here when we lose this leaving group, that's our secondary carbocation, which of course if we do a methyl shift, over here, we get the corresponding, oops, I drew that really poorly. Let's draw that. There we go. Draw the corresponding carbocation that way. Okay, our tertiary carbocation. Okay, so if we took this original thing and did our, removed a beta proton from that, what would it look like? Well, look at the 2 carbons next to that carbocation. Is there a proton on this beta carbon to eliminate? The answer is no, right? We've got 4 bonds already to that carbon, and none of those is a hydrogen. So you'd have to deprotonate from this carbon here. So your product from no rearrangement actually looks like this. Okay, you can see it's a mono-substituted, product that came from a high energy intermediate as opposed to the more stable tertiary one. Now with the tertiary one, obviously the Zaitsev product is much more common, but let's say we do get the Hofmann product here. We would, instead of eliminating a proton from this carbon, we'd eliminate it from one of these 2 carbons, which, they're identical, so it doesn't matter which one you do eliminate, but let's say we do that. There's your other product. Okay, so again, disubstituted not as good as tetrasubstituted, but that's why, it's a minor product. With the case of E2 mechanisms, when we look at the full picture with E2 mechanisms, basically we see that it's again a concerted step, right? We have our beta proton being removed by a base, and when it gets moved, we shift those electrons over to form that pi bond, which in turn causes the leaving group to leave. We can't have the leaving group stay when that pi bond is forming, because then that carbon it's attached to would be a Texas carbon. It would have 5 bonds. Okay, so the leaving group has to leave as those electrons swing over to form the double bond, to form the pi bond, and that, helps not violate the octet rule on anything. Okay, so yeah, so in terms of extra steps you would see, typically since your base is directing this, you typically have a strong base. So with your leaving group, can we use an acid to turn a weak leaving group like alcohol into a better leaving group? And the answer is no, right? You're using a strong base as your base. You don't want to use a strong acid as well because then it will, react with your base, and now you have less base available to do the reaction that you want. Okay, so something to keep in mind when it comes to selecting reagents. Okay, you want to typically have something that's a good leaving group already, because trying to improve it by adding acid might be a little bit difficult. So here's the intriguing part that connects us with the previous chapter. You've seen that, our conditions, or, like our starting point at least, for getting a substitution product versus an elimination product is kind of similar. We're starting off with the same substrates, really. So the question is then, what controls the products we form? How do we get a substitution product instead of an elimination product, or vice versa? If we want the elimination product, how do we avoid getting the substitution product? Okay, so you need to basically watch out for the conditions you're running your experiment under, your reaction under. Okay, so there are scenarios here where you get only one type of product. So, for example, here we have this tertiary iodide. We reacted with this, uh, with sodium methoxide and methanol, and we wind up getting only the elimination product via an E2 mechanism. But that being said, with different conditions and with the same substrate, notice that now we have a mixture of products. We have an elimination product via an E1 mechanism, and we have a substitution product from an SN1 mechanism. Okay, so again, you've got to be careful of what your reagents are. So to do this, okay, and getting this distinction, I think, is kind of important. Let's break down what controls are, the two pathways we could go down. Okay, so first of all, look at your reagent. Okay, so you've got your substrate, which is your molecule with its leaving group, but look at the other reagent you're using. Is it a base? Is it a nucleophile? Or is it both? So that's something to keep in mind. Now, secondly, of course, you want to look at your substrate. Now, we've kind of already done that a little bit when we looked at the distinction between SN1 and SN2, but again, you still want to do that here. Because again, we've seen that primary substrates are great for SN2, and that's it. All the other mechanisms prefer tertiary. So that's something to keep in mind if you wind up having a primary substrate. There might be a preference for a substitution reaction. Okay. Now, of course, then when you're looking, you need to determine the type of mechanism you're undergoing. Though, once you've determined that, that's going to play a role in what products you make. So you then want to consider the relevant, the regiochemistry and stereochemistry implications of the mechanism you're undergoing. Okay, and of course this can work backwards too. If you get a question that gives you the products and you say like, oh, I've got this inverted substitution product, that should tell you something, right? That tells you like, okay, I went through an SN2 mechanism to make this. So what conditions do I need to kind of force that SN2 mechanism, right? So your question can be asked in either way. It could either give you the reaction conditions, your substrate and the reaction conditions, and ask you what product would you make, or it'll give you your reactant, your product, and ask you, well, what happened? How did, what mechanism, went on here, okay, and what reagents might you need for that mechanism to occur? Okay, so let's break that down into each of those criteria. So that first one, and arguably the most important, is what is our reagent? Are we using a nucleophile, a base, or both? Okay, so remember, we kind of talked a little bit about this in the last chapter, but typically nucleophiles with a negative charge on them tend to be strong nucleophiles. I think if you go back to the previous chapter, we had a list of nucleophiles, and I kind of asked you to look at what all the strong ones had in common and how they were different from the weak nucleophiles. Okay, so you probably noticed that all of your strong nucleophiles had a negative charge. The ones that were neutral were neutral, but they had like a large squishy atom, like a sulfur, that can house a lot of electron density on it. Okay, so that's something to keep in mind for nucleophilicity. So, for example, a hydroxide ion way more nucleophilic than a neutral water molecule, which has an electronegative oxygen, yes, but that's a neutral. Whereas here we've got a formal negative charge on that oxygen. It really wants to seek out something positive to give those electrons to. Okay, so we've, and I think I've pointed out again, like, if you have a large squishy atom like a sulfur, that extra electron density, just makes it more nucleophilic. Okay, now the other thing that affects nucleophilicity that we didn't really talk about is the bulkiness of your reagent. Typically, if you have something that's really sterically hindered, that's really bulky, it's not going to act as a nucleophile very well. There just isn't a very good access for that nucleophile. The bulky rest of the molecule kind of stops that electronegative atom or negatively charged atom from really like kind of donating those electrons. So, so it's something to keep in mind there. Okay. Likewise, if you're dealing with a base, you might want to also consider, how strong a base are we talking about here? Um, and if you go back to chapter 3, you can do this either qualitatively using ARIO, or if you know the relevant pKa's of the corresponding acids for these bases, you can use that to help figure out which is, a better base. Okay, so for example, if we were comparing sulfuric acid with hydrochloric acid, you'll remember that sulfuric acid is 100 times a better acid than sulfuric acid, right? It has a lower pKa. That's 2 numbers lower, hence, 10 to the power of 2 or 100 times better. So now if sulfuric acid is a stronger acid, when we look at the conjugate bases of these two acids, which one's going to be a better conjugate base? And remember, it gets flipped here, right? So our chloride is going to be a better base because it is, from the weaker acid, so to speak. Okay? So it kind of works backwards there. I mean, I guess you could think of it kind of like as an equilibrium. If you have your acid, okay, but if you consider in retrospect your conjugate, I guess our conjugate A minus, that's going to be like a base in the reverse reaction, right? So and this is again very lazy, I should use water and hydronium, so don't mind that. But if HA is a really strong acid, notice that A minus is a worse base. Okay? So the more acidic HA is, the smaller and the worse that reverse reaction is, the worse of a base you're dealing with. Okay, so that's something to keep in mind. So the better your acid, the worse its conjugate base. Okay, so out of these two, chloride is the better base. That being said, of course, in this particular example, chloride and hydrogen sulfate are both they're both kind of awful bases, right? They come from really strong acids, so they're relatively weak as far as bases go to begin with. So, you're probably not going to encourage, use those as your bases for your elimination reactions. So with that in mind, though, like I said, if you don't have pKa's in front of you, you could then use ARIO to help determine that. Okay, so if it's, again, you've got to, breaks down depending on whether your base that you're looking at is neutral or has a charge, of course. Just as we practiced this back in chapter 3 when we talked about acids and bases. You can think of this in two ways. You could either think of, when determining, at least when we were looking at acids, you could either look at how good your negatively charged conjugate base is at stabilizing that negative charge. If it's great, then your acid is more acidic, right? If you started off with a charged species and your conjugate base is neutral, well, the other way to look at it is look at your acid that's charged and say, all right, how good is it at stabilizing this positive charge? If the answer is not very good, then it's going to be a better acid, right? So again, just like here with bases, we're going to do a similar thing. If we're looking at a neutral base, we ask ourselves, okay, what's the conjugate acid going to look like? Okay, is it good at stabilizing that positive charge we're going to put on it? Okay. Likewise, with a negative, like a base that already has a negative formal charge, when it picks up its proton, it's going to be neutral, right? So instead, let's look at that that charged molecule that has, that's acting as a base, and ask ourselves, how good is it at stabilizing that negative charge? Okay, so if it's good at that, then it has no incentive to act as a base, right? So, so yeah, so basically, so you can kind of compare molecules here and kind of figure that out. All right, so here we have some common reagents, and you can try to look at these and see what do we notice that these different groups have in common, right? Like when we look at things that act only as nucleophiles, what you know what is it about these molecules or these ions that causes them, that helps us recognize them as being only nucleophiles. Likewise, when we look at things that act only as a base, like what is it about them that does that? Of course, things get a little complicated when you have something that's both a strong nucleophile and a strong base. Okay, so here we have things that can work as both. We saw, for example, hydroxide early on in this chapter. It's like, well, metal hydroxides are strong bases, but we've also seen that hydroxide ion is a great nucleophile as well. Okay, then again, what does that imply for this distinction between a substitution versus an elimination reaction? Okay, and then of course we see like the protonated versions of those also can be weak nucleophiles or weak bases, which have their own set of problems as well when it comes to determining the product you're trying to make. So when you look at these, okay, so hopefully you've stared at these for a little while and sort of know some patterns here. But for example, your things that act as only nucleophiles, which prefer to act as nucleophiles, they have, we're looking at the conjugates of very strong acids, okay, like our hydrohalic acids, well, with the exclusion of fluoride, of course. And we're dealing with things that have, like, either they're large and squishy, like these sulfur containing compounds, or they have like negative charges on them. Yeah, actually, I think the negative charge one is probably not a great distinction because you can see here we have things that act as bases that do have negative charges as well. So, in the case of hydride as well. So maybe like don't go off negative charges, but I think the fact that we're dealing with things that are very large and squishy atoms, or they are conjugates of very strong acids, like the hydrohalic acids. When it comes to the molecules that act as, or ions that act as bases only, what we notice here is that, they're not as squishy, so to speak, as things that act as nucleophiles. So hydride, even though it's negatively charged, act as a base because it's essentially just a proton. It essentially just has, two electrons on it, right? You can't really like play around with that as much. So it doesn't act as a good nucleophile, even though it's negatively charged. Okay, but it does work as a base. It can pluck off a proton, and you produce hydrogen gas that bubbles away. Okay, so it's pretty useful in that respect. The other examples you might notice are very bulky. I mentioned earlier that bulky molecules don't make good nucleophiles. It's very hard for their electronegative atoms, or negatively charged atoms if they have them, to access your alpha carbon because of that steric hindrance. So you noticed DBN and DBU were acronyms that were listed on the previous slide as things being bases only. Here's what those stand for. Okay, so they're these larger, bulkier molecules, and with those larger molecules, you get larger names. So we use these abbreviations. But I guess instead of having to, if you don't want to memorize the names and formulas of these things, just generally remember if you have a bulky base, it's going to act as a base. Okay, it's not going to act as a nucleophile. Okay, now if you have a strong reagent, so something that's a strong nucleophile or a strong base, it's going to promote the bimolecular reaction. Okay, meaning like it will promote SN2 or E2. Both of those mechanisms are initiated by your nucleophile or leaving group nucleophile or base respectively. So it makes sense that if you have reagents that are stronger versions of this, they're really going to push that bimolecular reaction. Yeah, so again, like, there is some variance in here. I think they point out that tert butoxide is a base, but and it can be nucleophilic, but that bulkiness does make it more of a base, and therefore you're going to see more elimination than substitution. So even though it's included as both, I think it also depends on the type of substrate you're dealing with as well. Okay, so with a primary substrate, maybe it can act as a nucleophile as well. If you have a weak nucleophile, a weak base, for the same reason, since these aren't going to drive your reaction, if they're involved with one of your reactions, it's going to be either an SN1 or E1. It's going to be those unimolecular steps, because since these are not going to be involved in your rate determining step, you're going to have a mechanism that doesn't, have that in the rate determining step. Okay, so let's break down the different situations. So if you have a nucleophile only, it's going to do a nucleophilic substitution. That's your only option. Acting as a nucleophile is not going to act as a base, so you're going to get nucleophilic substitution. So going back to the previous chapter, what were the different, what would our substrate lead us to? Well, we saw that primary substrates pretty much always give us a nucleophilic substitution that's bimolecular, SN2 mechanism, whereas a tertiary substrate pretty much always gives us SN1. And of course, with a secondary substrate, we tend to have a mixture of products here. Okay, we're going to get both 1 and 2. So something to keep in mind again here. Okay, so looking at your substrate, which pathway are you going to go down? Okay, it's definitely going to be a nucleophilic substitution. The question is it going to be SN2 or SN1? Now, obviously then if you have a base only, well, it's going to do an elimination. So your options are all elimination reactions. Now, if you have an option between E1 and E2, since you're using something that's acting as a base, it's going to kind of direct that reaction. So you're going to get an E2 mechanism for all of these, essentially. In the case of something that acts as both a strong nucleophile and a strong base, you're going to get a mixture of products. Okay, if you have a primary substrate, I mentioned that your SN2 mechanism kind of takes priority there, so that's going to wind up being the bulk of your product. However, it's not going to necessarily be your only product. Since your strong your strong base, you still have a base present. It's still going to potentially pluck off a proton off your beta carbon. And that might initiate your reaction. You might see an E2 mechanism as well. Okay, but again, the primary substrate kind of promotes that SN2. Okay, whereas we've seen that even for E2 elimination, a tertiary substrate comes in handy. Okay, and speaking of tertiary substrates, again, you're going to see that E2 mechanism for a tertiary substrate, right? We don't really see that SN2 product, okay? And then, of course, with a secondary substrate, you still have a mixture of products, but again, now we're getting away from that primary substrate favoring an SN2 mechanism, so now that product is the minor product, the major product is the elimination product, okay? Until you get to like tertiary, where it's the only product, essentially. What if you have a weak nucleophile / weak base? Now you can see where these things get a little bit even less practical. So you're getting a mixture of products again, right? So even though in the previous example with a strong nucleophile / strong base, we're getting multiple products if we have a primary or secondary substrate. But at least the nice thing here is that we have a major product versus a minor product. Okay, so it's still practical in that you are making more of whatever you're trying to make. Okay, even though you're probably going to have a lower yield because some of it's yielding that other product that you don't want as much. The fact remains that you are at least getting that to be the product you want is still the major product. In the case of using a weak nucleophile / weak base, this is where things get impractical, right? You start getting large amounts of both products with a primary substrate. Same with with a secondary substrate, things get even messier. Notice that we have four different types of product here. We can make, you can essentially have our substrate undergo all four mechanisms, and therefore you're going to get a huge mess of products, of different products. And so the one you're interested in will probably make only a small percentage of what you get in this reaction. Okay? And so that's again, that's not practical when you're getting essentially small amounts of what you're trying to make. So basically, yeah, just consider now once you've determined which type of mechanism you're dealing with, then go back and think about the regiochemistry and stereochemistry implications. So, for example, with SN2, when you do an SN2 substitution, remember your nucleophile does a backside attack and gives you that inversion product. Okay, whereas with an SN1 mechanism, if you determine that's what's going on, you know you're going to get a racemic mixture. You're going to get a mixture of both enantiomers. Your nucleophile can attack either side of your carbocation. With E2 mechanisms, generally speaking, you've got to look at both your Zaitsev and Hoffman product and determine based on your reaction conditions which one's more likely. Okay, so remember your Zaitsev product is your thermodynamic product, your Hoffman product is your kinetic product, and that gets preferred if you use a bulky base to help drive the reaction forward. Okay, so a bulky base might give you the Hoffman product. Okay, and of course you want to like look at since with an E2 mechanism, it's a concerted mechanism that's initiated by your base, and that has your proton, and your leaving group leave concurrently. You might want to also consider, is there, let's say, an anti-periplanar hydrogen I need to get rid of, and things like that. Okay, if so, what's my product going to look like? What's the stereochemistry around it? Okay, am I getting the cis or trans isomer? That sort of thing. Okay, all of these things are things you want to keep in mind with your product. And of course, with E1 though, as we've seen, the Zaitsev product is generally it's pretty much preferred. You're going to get that Zaitsev product. Yeah, and again, like with cis versus trans, of course, trans is going to be usually more stable. And that's it for this chapter. So pretty much that's really what it comes down to. Like looking at your reaction conditions and saying, okay, based on this evidence, which way is this reaction going to go, and how, is it SN1, SN2, E1, or E2? And then you can use that to accordingly determine your products. Okay, like once you know the mechanism, you have a feel for what directs the product you make. Okay, so let's go through these practice problems and we'll call it a day. So go ahead and name these two compounds. Okay, so if you want the answers, here they are. Okay, so again, you want to identify, for the second one at least, identify your longest carbon chain containing that alkene. Notice that this is a chiral carbon, so we're going to need to name the stereochemistry on that, right? In this case, it happens using the Kahn-Ingold pre-log system. It's R oriented, right? You've got a methyl group, an ethyl group, and a larger alkyl group, okay, which would probably have the highest priority out of all of these. Okay, so yeah, actually, you have the high. I think if you got this wrong, if you got S, you need to remember that this methyl group's pointing away from you, and the hydrogen that's not shown is pointing towards you. So keep in mind to do this, you need to look kind of backwards on this molecule, essentially. Yeah, and let's see. Oh, don't forget your EZ notation. So, though they use Z, to be honest with you, they could have used trans, because we've got a methyl group here and a methyl group here. That's going to be trans notation actually, instead of being forced to use Z and saying like, oh, both of these high priority groups are on the same side. Okay. But I think it's probably more appropriate to say like, well, these are both methyl groups, so we've got to use cis-trans, and since these methyl groups are on opposite sides, that's a trans molecule. Okay. I kind of skipped over this one. Here we have a bicyclic compound. Again, notice that out of the 8 carbons total in this molecule, there are there's a double bond in there, so that makes this an octene. Okay. You named your alkene kind of using the same rules as we used for bicyclic compounds way back when we first started talking about hydrocarbons. Okay, so identify your bridgeheads that are here and here. Identify your bridge lengths. So there are 3 carbons in this bridge, 2 carbons in this bridge and 1 carbon in this bridge. Okay? And then, of course, name any other substituents, and if you're start from your bridgehead and go to your other one and number your carbons. So 1, 2, 3, both of your chlorines are on the number 3 carbon. Okay, let's practice leveling cis-trans isomerism and EZ isomerism. Okay, so go ahead and pause this video and see if you can name these. Okay, now there are some trick questions here, of course. You probably noticed with this first one, there are 2 hydrogens here, which aren't shown, so it doesn't matter which way you flip them, you're going to get the same molecule again. Okay. Here we have 2 fluorines on the same side, or 2 methyl groups. Here, actually, let me just put the answer up there so you can see them. So again, this one's neither cis nor trans. So both fluorines are on the same side, so we'd say that's cis. Okay. If we were using EZ notation, we'd call this Z, but like I said, I think using the moniker cis is more important here. Okay, since we're not dealing with identical groups, or sorry, different group, 4 different groups. Since we've got identical groups here, we can I think cis makes more sense. Okay. Likewise, here we have 2 methyl groups coming off of this double bond. So again, we can use cis here to show that they're on the same side. Okay, but if we were using EZ notation, this methyl group has higher priority over this hydrogen that's not shown, and this fluorine has a higher priority than this methyl group, and that's why, since the fluorine and this methyl group are apart from each other, that's the E notation. For this molecule now, when we look at this double bond, there are 4 different sets of molecules coming off of it. So this basically has, you can't really use cis nor trans, right? But you have to use EZ. So once again, we're going to assign priorities to these. So that's a fluorine versus this carbon, so that's going to have a higher priority. And out of these 2, the methyl group, of course, will have higher priority than the hydrogen. So both of these high priority groups are on the same side, or they're going to be the Z configuration. All right, here's our molecule. Go ahead and figure out what the E2 products are going to be. Okay, so hopefully you've done that. You'll probably notice that when it comes to kinetic versus the thermodynamic products, you're essentially looking at your Zaitsev versus Hoffman product, right? So when we take off this bromine, we're going to form a double bond either here or here. Okay. If we form it here, that's going to be the equivalent tetra-substituted double bond, which is more thermodynamically stable. But the problem is we're eliminating a proton from this beta carbon that has a methyl group on it, so you want to use a smaller base. If we use a bulkier base, it would prefer to deprotonate from this carbon and form the double bond on this side. So here's kind of circled which beta proton do we eliminate with our leaving group, our bromine leaving group, and where's the double bond we see. Okay, so here, like I said, that kinetic product is where this proton is easier to pluck off because there's no methyl group in the way. Okay, here, in this case, we're going to remove this hydrogen, which is this proton, which is next to a methyl group. So you get a smaller, smaller base for this. When you're looking at the stereochemistry of your product, don't forget that for an E2 mechanism, you're going to do an anti-periplanar configuration. So you've got to figure out where are your the parts of your molecule in space, right? How are they oriented in space? Do you have to rotate your molecule to get the hydrogen and your leaving group to be, anti to each other? So something to keep in mind. Okay, they kind of did that here, to get the hydrogen and bromine to be anti-periplanar. That being said, it's once you do figure out, what's going to happen, thinking about which direction your groups are pointing kind of tells you what the alkene is going to look like. So once you've rotated this so that this hydrogen and bromine are anti-periplanar, we know that we're going to form our double bond here, and if we're looking at this molecule, a group might be on our left or right, so depending on if we're looking down on this, okay, this ethyl group, the groups that are sticking towards us in this view would be on the person's left if their eye was up here looking down on this. Okay, so these groups that are sticking out towards us are going to be in the, you know, so the person's looking at it this way. So to see it this way, you kind of have to tilt your head a little bit to the left. But yeah, so notice that these ethyl groups are both together on the left, and this methyl group that's sticking into the board, which is on this person's right, is over here. So there's your, the resulting thermodynamic product, right? You're going to make that more stable tri-substituted product here. All right. So since tertiary substrates, well, this is again going to be a paragraph answer, but basically you want to think about what reagents will direct your, you want to, think about what encourages an E1 versus an E2 mechanism. So remember, your E2 mechanism is initiated by your base, right? So having a strong base can definitely be your determining factor. Let's have a look at this molecule and see what we're going to make. Okay, so we're using sodium methoxide. So ask yourself, what kind of mechanisms is this going to go under if you're using sodium methoxide as your base, since we're doing an elimination. Okay, and then like if it's going to be, where is that double bond going to form, right? Is it going to form over here or over here? Okay. Or if you're doing an SN1 mechanism, is it going to rearrange? So first things first is we realize we're doing we're using sodium methoxide as a strong base, so it's actually going to be an SN2 mechanism. So if it's an SN2 mechanism, we need to do an anti-periplanar geometry between our proton that we're going to deprotonate and our bromine, which the way it's drawn right now doesn't really show that. It's equatorial, so it's better to do a ring flip and have it in an axial position. Then you have to ask yourself, okay, out of your two carbons next to it, which one's going to have an axial hydrogen? Okay, so that hydrogen's sticking up there. Okay, so that's the one we're going to eliminate. So that's where our double bond forms. Okay, and this is what, if we take this out of this chair conformation, put it back into that sort of overhead view, this is what that's going to look like. And and that's what happened. I know I kind of like give the misleading, like, oh, what's going to happen if this undergoes an SN1 mechanism, but it's not. It's undergoing SN2, so that's why we get that product. Okay, and likewise, since this is the only option for an anti-periplanar proton, we don't have an anti-periplanar one on this carbon. This is the only product we see. Now look at these reagents. So here we're using concentrated sulfuric acid. Okay, so keep in mind that encourages our alcohol group to leave as a water molecule. So that's, and you get a carbocation. That's going to be an E1 elimination, right? So with that being said, ask yourself, what does that carbocation look like, and will it rearrange? Which hopefully you figured out that when you remove this alcohol group, this is going to be a secondary carbocation. If you do a hydride shift and move your carbocation to either this carbon or this carbon, now you've got a tertiary carbocation. So something to keep in mind. Okay, so that's what that looks like. Okay, we can get either side. We could have done a hydride shift from this carbon or from this carbon to give either one of these two. Okay, so something to keep in mind. And then depending on which protons you eliminate, you form the corresponding alkenes. All right, so finally let's try and distinguish between substitution and elimination reactions. Okay, so for each of these, have a look and decide from your substrate, from the reagents you're using, what are your products going to be. But in order to do that, you first need to probably think about what type of reaction this is going to be. So hopefully, let's list out the answers here so you can see them. Here we have a strong nucleophile, right? Sodium methoxide, so that's methoxide with a negative charge. That's going to be a strong nucleophile, and it's going to displace. We're dealing with a primary substrate here, which we know is going to favor SN2, and so that's what we kind of see. You don't need to worry about showing stereochemistry here. There's two hydrogens on this carbon, so it's achiral. So even though yes, it's a backside attack, you'd have an inversion of stereochemistry. There's really no way to see that inversion because those carbons aren't chiral. Okay. Now look at this one here. Here again we have sodium hydrogen sulfide, which is again a strong nucleophile, and you can see that we have an inversion product due to that backside attack. Now here we have sodium hydroxide. So hydroxide is interesting because it can act as a nucleophile or a base. All right. But notice that here we have a tertiary substrate. So we're probably not going to see an SN2 mechanism, right? But instead we see that our hydroxide can act as a base, and if this we take away one of these hydrogens here, we make this corresponding double bond here. Okay, and it's a tri-substituted double bond, so it's still pretty stable. All right, and that brings us to the end of this chapter. So if you have any questions, let me know. And this is the end of chapter 8, so that means we have an exam coming up. So please do the practice problems, the suggested homework problems. Of course, solutions guide's available if you want to check your answers. And let me know if you have any questions. Go through your old quizzes. I recommend doing that for chapters 5, 6, and 7. And of course, try the practice quiz for chapter 8 that I've posted on Blackboard. That'll give you a good idea of, if you look at what you got wrong in the quizzes and on the practice quiz, that'll give you a good idea of what you need to work on to get correct on the exam. Okay? All right, good luck.